So I'm here today to give a presentation to you guys, and the presentation is, who is this guy and why is he in my classroom? It's a fair question for you to ask. Why would I come back after a decade of being away from this school to give you guys a talk? And the reason is I'm here to sell you chemistry. Sell you science in general, but more specifically chemistry, and why you should go into chemistry, why you should pursue a field in chemistry. So a little bit about my background. I graduated from Foley High School in 2000. While at Foley High School, I was very into sports. I cared a lot about athletics. I was captain of the football team, captain of the track team. I was part of the football state championship team in 1998, state runner-up in the 4x200 meter relay, and the lowest grade I got in school was in chemistry. So how does one go from almost failing chemistry to being a PhD in chemistry? Well, it's an interesting tale. So I went on to St. Cloud State University after that, and I was part of the track team there. And because I was in sports so much, I ended up getting hurt a lot. A lot of injuries, you visit a lot of athletic trainers, a lot of physical therapists, and I actually ended up taking that path in terms of I decided I wanted to be an athletic trainer. Well, athletic training didn't quite stick for me, so I moved on to exercise science, didn't quite fit either, biomedical science. Finally, I ended up on chemistry, took organic chemistry from Daniel Gregory at St. Cloud State, fell in love with the field, and that's what I've been doing ever since. Yeah, this is me, and it says I can quit whenever I want. I'm addicted to science, that should be overabundantly clear at this point. But graduate school is basically research. What you want to do is research. So you start out, this is a 4 to 7 year process where you're doing research, taking a few classes. You actually end up taking classes only your first couple years of graduate school. This is where they re-emphasize and make subject matter more specific and teach you about it. You spend 1 to 7 years TAing. This is teacher's assistant, so you'll either supervise a lab or teach a lecture section. It's really simple stuff to do. Qualifying exams, this is presenting your results, defending your ideas. Research, that ends up being your entire span of grad school. You do full-time research. And thesis or defense. Sometimes thesis, defense, those are scary words. That is not the hardest part of grad school. If you get to the point where you're writing a thesis or defending your ideas, you have already passed. So it's taken me some time to really reflect on why I love this and why I love what I do. And the reason I'm back here is to share what I've gained, what I've learned with you guys. It's one of those, if I had known then what I know now, I might have been able to skip over a few majors type thing. So I'm going to share that with you. So first, let's start with the simple question. What is science? Flashbacks to like 7th grade science class, right? Defining what science is. Well, it can invoke imagery like this. Just a person in a lab coat staring at beakers, staring at vials. Alternatively, Hollywood has helped us out. We have perspectives like this, the weird scientist, gray hair, the Einsteinian look, or full-blown mad scientists, right? These are the images evoked when you think about scientists. And there are people like these, I promise, I know them personally. But in general, science is not this way. Let's simplify science quite a bit. So science is from Latin, scientia, meaning knowledge. Systematic knowledge of the physical or material world gained through observation and experiment. What does that actually mean? We can simplify it even further and break it down just to the scientific method. Observation, hypothesis, prediction, experiment. Now this is probably the most unappreciated aspect of human existence in terms of this is what you do all the time. You don't write it out, you don't publish it, you don't mix beakers together and do these experiments, but you do scientific method. It's not invented by scientists, it was formalized by scientists, but it wasn't invented by scientists. It's not limited to scientists. Every time you reflect on an experience and make a prediction about what will happen, you are doing scientific method. Your daily life, you come across some occurrence. Well, that's weird. Why did that happen? Why did something occur? I bet it's because of, well, congratulations, you've just formulated a hypothesis, an idea to describe a physical event. If that's true, when I do this, then this should happen. You made a prediction. You have a way to test it, and then you try it, and you find out if your hypothesis was correct. So I want you to think about this the next couple days. How many aspects of your life are dictated by this decision-making process? So let's use some examples of this. Tracking an animal. It's perhaps one of the biggest innovations in human history, being able to track animals. The reason we don't need to be fast as a species is because we're smarter than those animals. How are we smarter? If we see a footprint in the ground, we're making a lot of predictions. We're making a lot of hypotheses about what this footprint means. We can compare it to our hand and say, all right, if the fingers are going out that way, this animal is going in the upward direction on this slide. We can also tell based on this, maybe it's this type of animal. These are all predictions. These are all hypotheses. So cooking, this is a really great example. Essentially what we do in synthetic chemistry is cook. You mix things together, you get a product out. So if you're trying to bake a cake and you throw it in the oven, you pull it out, you end up with a solid block of glassy, sugary goodness. You could have a hypothesis in your head. You could say, maybe I used powdered sugar instead of flour, right? You have evidence, you made a hypothesis, you predicted that maybe you use powdered sugar instead of flour, and you can do an experiment. You can either do the same recipe and use powdered sugar, or you can do the same recipe and use flour. My personal favorite is video games. So when you really think about this, every time you pick up a video game, you're not just playing, you're figuring out the rules that govern the system. It's only through understanding the environment that you can really win at a video game. And the rules inside of a video game are not the same rules here. So essentially what you're doing is you're observing what happens, you're making a prediction, you're testing it. Every time you get killed by someone else, you are testing your prediction. This is scientific method. So if you really think about it, if you guys spend the next couple days really evaluating what you do and what your decisions are based on, more often than not, it's based on scientific method. It is experiment, it is hypothesis, it is prediction, over and over again. And this is all we've done as a species since the beginning of time. So if you go back to a more formalized version of this, we have a continuum of science. So basically on this end, we have the really small things, on this end, bigger things. So math, physics, chemistry, biochemistry, material science, all the way over to ecology, sociology, meteorology, economics, these really big systems that you're studying. The goal of all these systems is to be able to make a prediction. You're looking at experimental data and you're saying, all right, what's going to happen next? Now, the way we do this is in terms of equations. Do not let equations scare you. You're not experts in any of these. Don't worry about it. But the basic idea is every single one of these fields, you are trying to come up with some equation that says, if I put in these numbers, I know what's going to happen next. And the goal of science in its entirety is to put all of science on a single t-shirt. The idea that if you have a theory of everything and you have one equation, you can make predictions in physics, you can make predictions in economics, whatever it is. It's basically converging on one idea that will explain everything. Whether this is possible or not, we have no idea. Some people say it's not, some people say it is. We don't know, but we're trying to figure that out. Now, my particular flavor of science is chemistry. This is the one I fell in love with out of all the possible fields. I love chemistry, and it's broken down in these subcategories, but basically the common theme is we want to understand and manipulate matter on an atomic level. So if you take a look at your periodic table, you have 118 atoms on that table. If you look around this room, you see more than 118 materials. All right, how does that work? Well, most of the stuff around us is made up of this group of atoms here plus hydrogen. How does that work? What's the difference between you and I? It's the organization of these atoms. How do these atoms go together in specific ways to make us who we are? We're just a bag of chemicals interacting in certain ways, mostly water, other carbon, nitrogen, oxygen atoms. But that's what we are. And the difference is dictated by how these atoms are organized. Same thing for everything else you look at. Everything from rocket fuels to OLED screens, like I talked about, cosmetics, drugs, whatever it is. It's organization of atoms that make all of these things possible. Everything you see in this room is dictated by how their atoms are organized. And that is the field of chemistry. And that's one of the reasons I love it. So in terms of selling science, astronomy has a huge advantage in selling science. These guys like Carl Sagan, Stephen Hawking, Richard Feynman, Neil deGrasse Tyson, all these guys, astronomy is big. And you guys can see it, you can look up in the sky. In fact, we have a couple thousand years of sun worship. The reason we have a sun day is sun worship. You also have awesome imagery like this, Hubble Deep Field Image. They took the Hubble telescope, pointed it at a black chunk in the sky, and ended up with this. And you're seeing hundreds of galaxies on a single shot. Millions and millions of stars, and this is very grandiose. Unfortunately, when I'm trying to sell you chemistry, we don't necessarily get those grandiose images. You get stuff like this, beakers with different colors in it, which does not quite have the sexy allure that this image does. But we do have some cool looking stuff. This is actually called ferrofluid. It's magnetic particles suspended in a solution. As soon as you put a magnet underneath it, you can literally see the magnetic lines. So that's what you're seeing there. So we do have some awesome looking things, but not necessarily astronomy type grandiose imagery. So when I'm going to try to sell you chemistry, 3 ways I'm going to do it. I'm going to try to convince you it's fun, convince you it's interesting, and 3 subcategories are synthesis, characterization, and theoretical chemistry. And I'm also going to try to sell you the idea that it's important. I'll put a pattern on the board. Here's a number pattern. I want you to find the blank number. I'm going to give you 15 seconds to do this. It doesn't matter if you get this number. If you figure it out, raise your hand. Do not shout it out for me. So right now, everyone in this room's eyes are glued to that number sequence. Some of you, your eyes went really big and your brain was firing as fast as you can. All right, -9, +11, square root of 2, multiples. You did everything you could in your brain to solve that. What I'm trying to emphasize is this is science. You're trying to find a pattern and you're trying to make a prediction. Some of you guys really love the feel of this challenge, looking at a puzzle and trying to figure out how do I figure out the answer? Like those little toys where you have to get the ring off of a couple horseshoes or whatnot. This is what I do as a researcher. I look at a set of data and I'm trying to find a pattern in that data. Great part about science though is if you can't find this pattern, you can move on and collect more data. You can find more data sets that make that answer easier. Bottom one's 49, top one is 94. 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared. On the top, it's just those numbers reversed. So there's your answer. You did it. You found a pattern, you made a prediction, you just did scientific method. Great thing about science is you do not have to do this alone. I made you guys just do it alone, but you can solve it with other people. And these people are fun, entertaining, interesting people. And here's one example. So recently I got an article published in Journal of American Chemical Society, very prolific journal. First author on this paper is my name. What I basically did was I found a series of molecules and I made a prediction based on it. I did exactly what you did here. You'll notice the second name on this paper, Luke Roskop. Luke is actually one of my best friends from St. Cloud State University. We graduated together. I went on to University of Southern California. He went on to Iowa State. We met up at a conference later in New Orleans and I said, Luke, I have a problem, let's solve it. About 3 years ago, we were at his kitchen table in Anoka and we sat down together and we worked on a problem and we solved it. And we had a lot of fun doing it. And those results ended up in Journal of American Chemical Society. Not only you get to do that with friends, but you also travel a lot. So these are all the different places I've visited since being in grad school, and chemistry has paid for all of these flights. Because we're so specific and specialized in our subject matter, we need to get together as a group. There's only a handful of people on the planet that do the same research I do, and they're all in different locations. So what you do is bring everyone together in a conference, and you get to share ideas and exchange and present what you know, they present what they know, and you really start to talk about, all right, how can we solve problems? How can we create collaborations like Luke and I did? We were in New Orleans at the time. Some of the highlights from these journeys, San Juan, Puerto Rico, that was fun. It was for a meeting chemists plus engineers. We got together, we tried to solve some issues. Got to visit BioBay, rainforest, spectacular trip. Some of the other ones, a trip to Germany, University of Regensburg. During this time, I also went to Lindau, Germany. This is by far my favorite. I got accepted to a conference that was the 54th meeting of Nobel laureates in Lindau, Germany. So I got to stand in a room with 23 Nobel Prize winners in chemistry, rub shoulders with them, talk to them, hear them present. Absolutely amazing experience. In fact, here's a picture with me and Professor Robert Curl, 1996 Nobel Prize in chemistry for discovering the Buckminster fullerene. All right, it's interesting. So you guys haven't done a lot of synthetic chemistry, but here's a synthesis, SN2 reaction. It's called a bimolecular nucleophilic substitution. This is one of the first things you'll learn in organic chemistry. And the way this reaction goes is you take something like ethyl bromide, you add hydroxide, potassium hydroxide, sodium hydroxide, whatever it might be. The hydroxide attacks that carbon, kicks off the bromine, and you end up with this species, ethanol and then bromine in solution. This is a reaction. This is the way we draw reactions in chemistry. Arrows tell you where things are going and what happens. Now, it's very easy to draw this on the board and say, well, look at that, that's interesting. But it's much bigger than that. Because when you think about what you have going on, you have a solution of this hydroxide, a solution of this ethyl bromide, we'll say 1 gram. You have 10 to the 21st molecules. That's 21 zeros doing exactly what you want it to. It's not just one molecule interacting with another. You're controlling all these molecules together to make an outcome that you want. So if you take 1 gram of ethyl bromide, end up with 0.43 grams of ethanol, that's 5.6 times 10 to the 21st molecules doing exactly what you want them to do. Let's think about this a little further. So here's a drug, Lipitor. You guys might have seen commercials of this. It's for lowering blood cholesterol or whatnot. The way this is actually made is from very simple starting materials like valine. Very cheap, inexpensive. You can get a hold of this readily, but essentially what you do is a series of reactions like this to build it into something big, something expensive, something worthwhile. This is as close as you will ever come in your life to being a wizard. Think about it. You're mixing things together and you're making matter do exactly what you want it to do. That's a pretty magnificent power if you think about it. We can do what nature can do and we can do it better. So characterization, here's another aspect of chemistry. It's basically, you can make things, but you also need to know what those things are. You need to understand the environment around you. So here's one example, atomic force microscopy. Basically, if you close your eyes right now and put your hands across your desk, you could figure out what's on your desk, right? You could feel it, you can map it out with your hands. We do essentially the same thing, except here you use a gold tip and you end up with one gold atom. On the end, it's a carbonyl molecule. And you have molecules on a surface. And essentially what you're doing is just poking that surface and seeing what's on the surface. And you end up with imagery like this. This is a molecule, penicillin. This is the way we draw it. This is the way it actually looks.